Thanks for joining us for this tutorial for the construction of a landfill simulator. Before we begin, let's acknowledge the incredible contributors to this project from top left to bottom right, Dr. Julia Devoy, D.L. Lumberg, Eva Autumn, your narrator, Evan Warrens, Elizabeth Conjusta, and Seraphin Dyson. In the top right, we'd also like to thank Boston College and the Ignite Grant for making this research possible, as well as our collaboration with MFC, or Make Fashion Clean.
The global textile trade has far-reaching impacts beyond the size of our wardrobe, and that is clear to see when one truly looks at its reach. This graphic here shows the net imports and exports of textiles across the world by country. This is calculated by subtracting the pounds of post-consumer textiles imported from those that are exported over 15 years. Here, red denotes a surplus of exported post-consumer textiles, meaning that these countries are shipping their textiles out to other countries, while blue denotes a country that has brought in more post-consumer textiles than it has exported. Countries in red, like the US specifically, and many other Western countries, are continuously sending out more and more of their post-consumer textiles across the world, with no signs of change in behavior. This second visualization really hones in on and solidifies what we were looking at on the last slide. We can see here that regions reaching to the left with negative net imports are sending billions and billions of pounds of post-consumer textiles out across the world. Western European and North American regions continue to send out more and more textiles each year, while developing regions such as Eastern and Western Africa and parts of Eastern Europe are being forced to take on the burden of handling these textiles. What we are seeing here are the countries and regions that are some of the highest exporters of post-consumer textiles in the world. This is shown reflecting the pounds of consumer textiles exported per person, removing the effect of population size. From this graph, we are seeing a general upwards trend in textiles exported per person from 2001 to 2015. This is detailing the trend of fast fashion that has taken over consumers' wardrobe choices. As consumers continue to be pressed to continually update their wardrobes, outdated clothing items must go somewhere, and these are often ending up in distant landfills. As shown in the previous visualizations, Eastern European and West African countries are those that are most often receiving these textiles. This creates a problem, as these textiles are often disposed of and placed in simple, uncovered landfills. These landfills are open to the environment, allowing leachate and gas from the breakdown of textiles to penetrate the groundwater and air. The current effect of this decomposition on the natural environment is unknown but potentially massive. From this, we believe it to be crucial to be able to quantify the impact of textile decomposition on the environment in order to better inform consumer behavior and policy to reflect the dangers that this trend poses. With all of this in mind, the immense environmental implications of the current textile trade are incredibly salient. By the tons, clothes are exported from Western countries, and they are left to degrade in foreign open landfills, releasing dangerous gases and leachate. Hoping to quantify these negative effects of textile degradation, we encounter the idea of a landfill simulator, a completely sealed-off bioreactor that is used to model the biologic processes that occur in landfills. Now, this is not a unique idea, but we had a couple unique requirements. Looking at previous literature, we saw that landfill simulators previously designed were massive outdoor installations, or they were small lab bench scale short-term devices. And neither of these scenarios really fit for us, as we needed a long-term design that could model the almost year-long process of textile degradation that could also be moved and stored inside if need be. These landfill reactors were also traditionally incredibly expensive to produce, and as a result of this, we decided to take matters into our own hands and design a landfill simulator that would fit all these criteria. As we worked on this project, we began to see just how cost-prohibitive science research can truly be, and we found a second defining characteristic of our project, that is, frugal innovation, wherein we are modifying existing designs to make them more accessible and affordable to all while preserving their functionality. We designed a landfill simulator that can be made at a fraction of the cost of traditional designs and is constructed from commercially available materials. In this way, we are opening the door of this field of research to those traditionally excluded by the cost or accessibility of science, and we are able to put these tools in the communities most impacted by the global post-consumer textile trade.
My name is Eva. I'm a senior at Boston College, and I'll be walking us step by step through how to build a landfill simulator. The purpose of a landfill simulator is to investigate the effect of textile waste on the environment by characterizing chemical leachate and gas production from textile waste decomposition within a bioreactor simulating landfill conditions. Wow, that's a mouthful. There are a lot of components, so for now let's set aside the gas collection and water circulation system and just focus on building the frame. Please wear personal protective equipment, like gloves, and when we're handling an electric saw, glasses and a mask so nothing flies into your mouth or eyes. Let's get started. This tutorial is divided into 4 parts: construction of the main body, the bottom port, the top port, and the sensor container. We will need the following materials in the construction of our landfill simulator, as well as 2 larger pieces, a 2-inch diameter PVC tube and a 4-inch diameter PVC tube. For plastic-to-plastic connections, we'll be using PVC primer and cement. Remember your personal protective equipment, and it may be helpful to have soap, a pencil, and tape measure handy. For the main body, you'll need the 4-inch in diameter PVC pipe, and in this case we went with a clear pipe so we could see the experiment as it's running. We'll also need 2 4 to 2-inch rubber reducers. We measured the pipe to 4 feet, but feel free to change the height according to your experiment's parameters, and then use the power saw to cut the pipe in half. The place you saw will have rough edges. These are called burrs, and it's a problem because they catch on things or might get loose. So we'll sand the burrs off. This is called deburring. See the difference? Next, we'll fit our 4-inch to 2-inch rubber reducer on one end of the clear PVC. For this, you'll need a screwdriver and a lubricant. I'm using soap. To make it easier, we'll remove the steel clamps, then soap up the 4-inch side, which is where the rubber reducer will connect to the pipe. It is a tight fit, but it may take some time. So as the Russian writer Leo Tolstoy said, the 2 most powerful warriors are patience and time. Once it's on, we'll add the steel clamp back and tighten it to secure the connection. Then we'll do the same on the other side. Nice work! Part 1 of the construction is done. Give yourself a thumbs up. Next, we'll construct the bottom port. Its purpose is to be the outlet that pumps the water that's leached to the bottom of the landfill simulator. This piece consists of a bushing, nipple, small valve, and adapter on the side opening, and a plug on the bottom opening. The top opening will connect to the other end of the 4 to 2-inch reducer later. This is the T, the bottom plug, and the bushing. We also have PVC primer and cement. These bottles can be hard to open, so I use the rubber end of shears. We'll apply a layer of primer to where the plastic fittings will connect. And the purpose of this primer is actually a chemical reaction that softens the PVC and prepares the surface for the cement. Now let's wait 5 minutes for the primer to dry. Next, we'll apply a layer of PVC cement, a white, gooey substance. This melts a thin layer that solidifies after being put together, forming a waterproof seal. After fitting the connections, the cement requires 2 hours to dry. But you don't need to wait that long to get started on the next step. We'll use the following items next. First, a nipple. Second, a ball valve. And third, an adapter. Finally, a wrench, if you'd like. These materials are threaded, which is why they fit together easily and form a seal without cement. Don't use the wrench on the nipple since it's made of plastic. It will actually strip the material and make it unusable. The purpose of the ball valve is to maintain a closed system for when we need to adjust the tubing it's connected to, like moving the tubes to sample leachate or add water to simulate rainfall. A simple turn will either seal or unseal the system, so when we adjust the tubing it's connected to, there's no risk of contaminants from the outside. Last, we'll add the adapter, which will connect the ball valve to the pump's tubing. Our third component is the top port. The side opening will be an inlet for water to be pumped into and leached through the landfill simulator, while the top opening will be where we add the gas collection system. Both openings repeat the fittings from the bottom port. The only difference is we're using a cross instead of a T, The other two openings will connect to the sensor box and the main body. Let's apply the PVC primer first. Then we'll wait 5 minutes for it to dry. Next, we'll add the cement and fit the pieces together. We'll repeat the nipple to ball valve to adapter connections on both bushings. Nice work! Our last component is the sensor container. This will house our Arduino sensors, which will measure and wirelessly report conditions within the landfill simulator like temperature, gas concentrations, and pressure. We'll insert a plug on one opening of the sensor box, and a PVC pipe, large valve, and PVC pipe connection to the other. The sensor box will then fit into one of the openings on our top port. This is what the inside of the sensor box looks like, and it's where the Arduino sensors will be kept. A gasket and screws will seal these sensors inside and prevent anything from outside of the box to get in. Thus, the sensors will only measure the conditions within the landfill simulator. Let's hear from Evan Warrens about the Arduino sensors.
With the landfill simulator built, we had a very effective way that we can model the biological processes that occur during the degradation of textile waste in landfills. But we wanted a way to be able to quantify those variables, such as the release of greenhouse gases or any changes in temperature that are produced. And so we needed to think of a creative way to do that in this completely sealed off environment that we created within the landfill simulator. And we ended up doing that through the use of this unassuming gray conduit box. So right now we're looking at the outside of the sensor box that contains all of our sensors for this project. And you see it'll be connected via this port to the greater landfill simulator. So it doesn't really look like too much from the outside, but when you get a peek under the hood,
just removing these two screws,
you see there's really a lot more going on in there. And there is an Arduino microcontroller unit along with all of our sensors that we were using to measure parts per million CO2 and methane, as well as the temperature, humidity, and pressure of the unit. And they're all connected via a breadboard that permits really easy solderless connections so that we can very quickly change out these sensors, put in different ones in case we ever need to change some experimental parameters. So what I have here is a very small, but no doubt crucial sensor for our entire project, and that is the MQ4 methane gas sensor. And so this, as you can see, isn't very large. It's only about 1.5 inches by 3/4 of an inch the other way. And it is able to detect concentration of methane in the air based on an electrochemical detecting principle. So basically how that works is that there's a very small piece of metal inside of this unit in here. And as the concentration of gas in the air changes, specifically for this unit methane, there is a change in the resistance across that piece of metal. And that change in resistance is then read in by the Arduino microcontroller unit and is read against a calibration curve that is then able to turn that into a parts per million concentration of CH4. The next sensor we have is the MHC16 CO2 sensor, and it's actually made out of two parts. We have the probe here, which is a couple inches long and still fits in the palm of my hand. And then we have the much smaller sensor chip. And so this is a NDIR, or non-dispersive infrared radiation sensor. And so the way that works is that this is exposed to the environment that we're trying to test, and some CO2 travels in through these channels and remains within this probe. And so then the probe sends out a beam of infrared radiation down here, which is then reflected back, and that is sent back to this sensor chip. And so the concentration of CO2 in the air affects how much of that light is sent back and how much is received by this sensor chip. And so then that sensor chip is able to read that and send it to the Arduino unit as a voltage signal, which can then be turned into a CO2 parts per million concentration. So what I have in my hands here is the BME 280 environmental sensor. So this is another small sensor. It's about 2.5 inches by 1 inch this way. It may be small, but it's definitely super important and super powerful. So this actually does a couple useful things for us. It can read temperature, humidity, and pressure. In our case, we're using it to read temperature and pressure within the landfill simulator. And then that data is sent directly to the Arduino microcontroller unit where we can access and analyze it. So the final piece of the sensing puzzle is the microcontroller unit. And this serves as the brain of our sensing system. And it collects all the information from the different sensors and then sends them to the internet to store them where we can visualize them and analyze and work with them. And so this is the Arduino Uno Wi-Fi Rev 2, which is a really similar board to the very popular Arduino Uno, which is just a very versatile and very user-friendly microcontroller board. And so this is different from the Arduino Uno in that it also has an onboard ESP Wi-Fi module. And so that makes it really simple to connect this board to the internet and send information over the internet. And so that allowed us to really be able to focus on just the sensing portion of this project and getting all the measurements correct and making sure that the data is valid and one that we can use.
Let's return to construction. A large ball valve will separate the sensor container from the rest of the landfill simulator. In the event one of the sensors stops working, we can close this valve and open the sensor box to fix the problem without interrupting the experiment. Sections of the 2-inch PVC pipe, primer, and cement will seal these parts together. We can measure out the 2-inch PVC pipe into 3-inch pieces. Then, use an electric saw to cut them. Remember to use personal protective equipment. We can deburr our pieces afterwards. Let's add the plug to the bottom of the sensor box with primer and cement. Next, we'll add primer to the remaining connections. Wait 5 minutes, then seal with cement. And now, let's finish the remaining connections. Now that we've constructed the main body, bottom port, top port, and sensor container, let's bring it together. The top port will attach to the top of the main body, the sensor container along with it. The bottom port will attach to the bottom of the main body, and a tripod will be used to stabilize the structure. Thanks for watching this video, and we'll include more later as we complete our work on this project.